So we will all recall that we discussed trees last week. We defined what trees are. We defined height and depth. We looked at a few traversals, pre-order and post-order. Then we moved on to binary trees. We looked at what a pre-order and post-order traversal of binary tree looks like. We looked at a few applications. And then we discussed an in-order traversal, and we looked at how that could be used to print out a tree correctly. Right. So we're going to continue from the next slide. This will be the last type of traversal we're talking about for now, which is called Euler-Tour. Some of you will know that it's not actually pronounced Euler, it's Euler. I was taught Euler and it's stuck, but do better. So when I talk about Eulerian tour, it's actually an Eulerian tour, and Euler is actually pronounced Euler. Right, so this type of traversal can actually be used, it's a more generic traversal that can actually be used to implement any of the others that we've discussed thus far. Um, and if we only implement certain visits of this type of tour, it will be equivalent to the in, pre, and post order that we've discussed thus far. All right. However, it includes all of these, so it actually requires us to visit each node not once, as we do in any of the other traversals, but to visit them thrice. And each visit is differentiated depending on which visit it is. We have a first, a second, and a third, and we call that the first visiting on the left, the second visiting from below, and the third visiting from the right. And we see that this actually makes perfect sense if we look at this traversal starting at the root, right, our special node that doesn't have a parent, and traveling through our tree along the leftmost branch of that tree, that edge, and then going around our tree. So let me just annotate this so we can understand what we're discussing. We start over here. You note we visit this root node from the left if we're doing this type of traversal, which is kind of shown here by this hatched line. So we visit this root node on the left first, then we get to its left child. We visit that on the left first, then we get to this leaf, which we actually, or external node, which we visit from the left, then underneath, then right all at once because it has no children. Then we go back to its parent, we visit it from below, then we visit the right child of that node from the left, then for each leaf, left, below, right, then its parent from below, then this one from the left, below, right, then its parent on the right. And then we go back to that parent, which is the left child of the root, visit it on the right, then visit the root from below, then visit the right child from the left, this external node from the left, below, and right. Then we visit the parent of that node from below, then the right child of that node from the left, then below, then on the right, visit the parent that was the right child of the root from the right finally, and then the root from the right. So you'll note we visited each node 3 times. We have 1, 2, 3, 6, 7, 8, 9. We have 9 nodes here, and we've actually done 27 visits. For each one, we visited on the left, and then from below, then on the right. If we were to do something only when we visit the node from the left, then it will be equivalent to a pre-order traversal. If we were to do something only when we visit each node from the bottom, from below, then it would be equivalent to an in-order traversal. And if we were to do visits only from the right, then it would be equivalent to a post-order traversal. So that's why we're told that it's a general one and can actually do any of those types of visits that we discussed before. But if we also decide to do specific things, different things, for each type of visit, we can do more general things, and we'll look at an application just now. I hope you all understand how it works. We're visiting each node starting from the root, and each time we visit a node, we do a different type of visit from the left, from below, from the right. What those actually are, as we've said before, is up to us. What work we determine we want to do each time we visit a node is really up to the application that we are trying to create to solve some problem. So what would this look like in pseudocode? Well, Euler tour of this tree T starting at node V, which could be the root. or could be some subtree rooted at V, but it is a tree regardless. We'll begin with a visit on the left of V. Then if V has a left child, right, remember that we were dealing with a binary tree, we have to loop through all the children. We simply check, is there a left child, then do the appropriate if there is there a right child, do the appropriate if there is that. So if it has a left child, then recursively call Euler-Tour on that left child of V. Then we visit V from below. Then if V has a right child, we recursively call that Euler-Tour on the right child of V. Then we visit it on the right. So note, if it's an external node, then that will be false. That will be false. And we simply end up visiting V from the left, then from below, then from the right. Okay. So we're going to use this type of traversal, this Euler-Tour, to print out an arithmetic expression. Now we have to decide, well, what are we actually going to do when we visit each node? And of course, what should we do for the different types of visit? So here we're going to agree that when we visit a node from the left, we'll check if it's internal or external. If it is internal, then we will print a left round bracket or a left parenthesis. Then when we visit it from below, we'll print whatever is stored there, either a value or an operator. So if it's an external node, we will print the value that's stored there. If it's an internal node, we'll print the operator that is stored there. Then when visiting from the right, again, we will check whether it's internal or external. If the node happens to be internal, we'll print this right parentheses, this closing parentheses. If it's external, note that we do nothing for the left and right visit. We only do something for the visit from below. But for internal nodes, we do different things for each type of visit. All right. So we already looked at what an expression stored within a binary tree would look like. We said that we could use our post-order traversal to actually evaluate one of these. But what if we'd like to print that expression that is stored within a binary tree? Then by following the rules that we have agreed on in the previous slide, we can do exactly that. So let's convince ourselves. We begin at the root. Is the root internal? Yes, certainly it is. So we print an opening brace there, or an opening bracket. Then we travel along the left side as we're trying to do this Euler-Tour. We get to its left child. Is it internal? Yes. We print another opening bracket. Then we go to its left child. Oh, it's external. We don't do anything for the left visit. For the visit from below, we print or retrieve or whatever we're going to do with its value there. Here we'll print it to our string. From the right, we do nothing because, again, it's external. Then we visit its parent from below. That is internal, so we print the operator stored there. We then visit its right child. It's internal, so we have to print that opening bracket for our, if we're visiting it from the left. Then we go to its left child. It happens to be external, so we simply print the value that's stored there. Granted, it happens to be a variable, but it is a value. Then we visit it from the right. Nothing happens there because it's external. Someone asked, internal has children, external doesn't have children. Yes, that's exactly what we agreed. External, also known as a leaf, means it does not have children. Then we visit its parent from below. It's internal. We print the operator that is stored there. We visit its right child. It's external. So we do nothing for the left visit. Print out its value for the right visit. Nothing for the right visit. Then we visit that parent. It's internal. It's a visit from the right for the first time. So we print that closing parentheses. Then we visit its parent. Again, exact same situation. Happens to be internal. We're visiting from the right, so again, that closing parentheses. Then we're visiting the root from below. That means we print out the operator stored there. We visit the right child from the left, so we print out that opening parentheses. Then we're visiting its left child. It happens to be external. We do nothing from the left, print the value from below, and then do nothing from the right. Visit its parent. Again, it's internal. We have to print the operator stored there. We go to the right child, it's external, do nothing from the left, print the value stored there. When we visit from below, from the right, do nothing again. We visit the parent from the right, it's internal, we print that right or closing parentheses. We go to the parent of that, which happens to be our root. Again, it's internal, so we print that right parentheses. So by following this Euler-Tour and sticking to the convention that we agreed, that a left visit, if internal, is that opening parentheses. If it's external, we do nothing. A visit from below, we print either the value or the operator stored there, depending whether it's external or internal. Then a visit from the right, for external, do nothing. For internal, print exactly, or we print that closing parentheses. All right, let me look. There have been a couple of questions that I've been discussing. Okay, actually, those have been answered, most of them. The last question, can we go through the height and depth of this binary tree? All right, so let's look at some examples and answer those. All right, I'm gonna remove the annotations that we have thus far. Then, what would the depth of this node be? In fact, let's pick a random node here. I want to know, what is the height of that node? What is the depth of that node? All right, and in fact, since we're going to be discussing the test after this, I am going to allow you guys to draw on the whiteboard. So, or files as well. So whoever wishes to answer that can actually use their mouse and actually draw on the whiteboard there. All right, someone has already given answers. You can go ahead and write it so everybody can see. Okay, I just see emojis. Great, thank you. So the height is 0. Why is the height 0? We agreed that the height is, how do we define height? We happen to define it recursively. You will recall. We said that the height of any node is equal to 1 plus what? Okay, you're going to be asked these things in 2 days, so I'd hope that there would be a flurry of answers here. Okay, max height plus 1. Another says max child. Okay, if we combine those two, we get the right answer. The maximum height of any of its children plus 1. All right, so this one, which contains 3, happens to be external node and external node. So the height of its children are non-existent. All right, so its height is 0. Then, that's correct. The depth, again, we defined recursively. We said that it's the parent's depth plus 1. So we go to its parent, we say, what's your depth? It has to ask its parent. Its parent happens to be the root, which is actually the base case for our recursive function that gives us the depth. So the root's 1 is 0. 1 plus that is the height. Let's just actually write this here. Root's height is 0. 1 plus that is the height of the parent. And so 1 plus that is the height of the child. Right, I was saying height now, depth, moving downwards. So root's depth is 0. That right child has a depth of 1, and the left child of that has a depth of 2. All right, so great. That was 2 correct answers. That'll get you marks for the test. All right, so this is simply pseudocode for exactly what we did. Surely we all understand this. For that left visit, we would first check, we've replaced left visit with what we've agreed should be done for a left visit. Check if it's internal. Note there is no else, so if it's external, we do nothing. If it's internal, print that opening parentheses. If it has a left child, recursively call the method on that left child. If it's internal, now this is our visit from below, we print the operator value stored at the current node. Then check if it has a right child. If it does, recursively call the method on that child. Then we do the visit from the right, and we simply print, or first we check whether or not it's internal. If it is, we print that closing parentheses. All right, let's pause. There are a couple of questions. What do T and V represent? T is the tree, V is the node, so we're basically saying V in T, all right? T has such methods as is internal, that it can ask us, we can ask, is any node internal for this particular tree? All right. You can also ask, does it have a left, does it have a right, so on and so forth. You note there that we also call, when we recursively call, it's still within the same tree, so you'll see we still use T there. We're calling that left method on V, and so that'll actually return to us and a reference to another node, which happens to be the left child of V. All right, next question. I really didn't understand. Please repeat. Is that the depth and the height? All right, we can do that again. Then, if you add 1, how is it 0 and not 1? What are we talking about here? Let's go back. All right. You recall that for a recursive function, we have a base case. Then any other case should move towards that base case. So let's note, for depth, our base case is if that node is the root. And if it's the root, its depth is then, is then equal to 0. For our height, the base case is it external? And if it's external, then its height is equal to 0. All right. So if it had children, we would actually then check what maximum height of those children is. However, because it is an external node, right? So perhaps that question shouldn't even ask the question before we ask what the maximum height of its children is to actually ask, is it external? That will be our base case. That will be our base condition. And if it is external, then we say that its height is 0. Similarly, for depth, is it the root? If it is, then its depth is 0. Then let's do one at a time because we don't want to combine these two ideas. For depth, let's look at the depth of this one, of 2 in that left branch. We say that if it is the root, its depth is 0. Otherwise, it's 1 plus the depth of the parent. Is 2 the root? No. So we go to its parent. Again, is it the root? No. So it's 1 plus the depth of its parent. Its parent has a depth of 0 because that is the root. So the depth here is equal to 1. That then returns 1, and so the depth of this one we calculate to be 1 plus 1, which is 2. Right, so because the base case, we say 0. Similarly, for our height, let's say we wanted to find the height of this node, that is an internal node storing that subtraction sign, we say, well, the height, is it external? If it is external, its height is 0. Otherwise, the maximum height of any of its children. So we recursively call that method on its children. The children do satisfy the base case. Both of their heights happen to be 1 because, happen to be 0 because they're external nodes. Then what's the max of 0 and 0? 0. And so the height of this one simply becomes 1 plus that 0. There we go. All right, so I think what you were talking about was when I asked the maximum height of any of his children. It didn't have any children, so it actually satisfies our base case, which we agreed is then 0 for the height. Okay. So we note that this is actually an application of the template method, which I'm sure you learned last year, which is simply a pattern that you must have discussed before, which says that we're able to actually define a method that relies on some implementation that is not yet done. Let's go back to see if this is actually the case. That here, we could have written this down in pseudocode or actually in code. We are calling these methods on the left, from below, and on the right before we actually define what those are. So here, this is a concrete method. However, it relies on the implementation of all the methods that it calls without actually giving those implementations. So at this point, if we were trying to do our printing out an expression stored in a binary tree, we could create this concrete method to do that. We would actually have to go eventually and actually implement those visits from the left, visit from below, and visit on the right. Even though this is not an abstract method, it is a concrete one. And we could do that based on what parameters we're passing to it. So we could do more than simply give a single implementation from each of those. We could give different implementations based on what, I went too far there, based on what we're actually passing to it. But and so we could do more specialized steps based on that. But for the implementation, we're simply saying, okay, here, this requires something else to exist and not define them first. If we're to have everything in the same class, then yes, those would have to be abstract classes, which makes all the abstract methods, which makes our entire class abstract, and then whichever class actually implements that will have to, or extends that rather, will have to give implementations for those methods. All right, in this particular case, that's what we're doing with the left and the right. We would then have to implement those, and we could do those for specialized objects based on those objects types. All right, so that should hopefully tie to something you already know and have it make a little more sense for us. Okay, so now the time you're waiting for has arrived. We said that we would. I just note that there are some exercises here. I updated these to be the ones in the new text. So in preparation, you can certainly go and take a look at those. Some are actually quite interesting, especially the creative exercises one. So go and have a look at those, and it should test your understanding of trees and the ideas that we have discussed thus far. All righty. Well, pros and marked. We're actually just about done with them. Should be done by tomorrow. But Prof. Van der Haar has gone ahead and made that video that was promised based on the ones that he had covered thus far. So if you go and check the video, it's rather specific. Go and check that. And if your idea satisfies those requirements, then go ahead and get started. If it doesn't, then you know what you have to add or change for it to satisfy those requirements. Right? That is really the outcome of our analysis of the proposals that have been handed in. And each year, the video really does depend on what issues we have picked up, what common mistakes we've seen within the proposals. And that then allows you to be able to take that, make sure that your idea satisfies those requirements, and you can go ahead and get started. But we will. Okay, please don't just put annotations on there unnecessarily, but we will give you that formal feedback very soon. So we were asked or requested that we go through a previous paper. As I said, this is the first time that the first semester test will be done remotely, so it will be a bit different, but there certainly are a fair number of application questions here. So we will all benefit from discussing these. And the first one happens to be now. Okay, can you hear me now? Yes, okay, good. Thank you for that. All right, so I was just asking who would like to answer this for us, and simply saying that I will first confirm that you are still allowed to make those annotations, and yes, you are. All right, so is there anything wrong with this? That certainly doesn't require an annotation just yet. Do we think there's anything wrong with this code, yes or no? Yes, yes, yes. Justify your answer. So what is wrong with this code? The I not being initialized to a value. Okay, good. Though the default value would be given there when it's created, so it still work, but yes, you get a mark for that. What else do we think is at fault here? What else are we trying to do that we really should not be trying to do? Can't directly create a generic array. Yes, so we can declare an array of generic type. So here, that generic type parameter is T. We can, let me just highlight this, annotate that. This part of it will work. You can create that, however, or rather declare that type. However, we can't go ahead and create an array of generic type. So that would not have worked. All right. Then provide source code that will fix the problem. Well, you could follow the route you were taught, where you'll create an array of object type and then cast that to that generic type. All right, and for the other issue that was picked up, that I has not been initialized to some value. If we're trying to traverse the entire length of an array and print out what's stored at that array, then we would also initialize I to 0 first, so that we print out each index and the value stored at that index for our array from 0. I see that there's a lot asking me to zoom out. Is it that it's too zoomed in for you guys? Let's agree on that now. Does that suffice, or is that still too zoomed in? Oh, wow, someone's actually asking me to zoom in or zoom out. All right, I'm gonna leave it that simply because it seemed like it was a bit too zoomed in for others before that. So that's kind of midway. Okay, and someone has given a better answer for that. It's up to you to decide your view controls, and that does not affect the other. All right, then the other questions, let's see. New operator, object-oriented design principles, inheritance, flow control. So you wouldn't really get these types of questions simply because you could easily look these up, right? Though these are all things you should know. We had agreed that the new operator does 3 things. What are those 3 things? So the full question is, in Java, a new object is created using the new operator. Discuss 3 events that occur as part of the creation of a new instance of a class. And someone's already answered all 3. Block of memory is created for the object. Yes, so memory is dynamically allocated. The object is then initialized. So the relevant constructor is called and meaningful values are given to those. And then, well, initially in that creation stage, they're all given default values. Then when the constructor is called, they're usually given meaningful values. Then the object is then assigned so block of memory that was created. That third one is actually that a reference to that new object is returned. And usually, yes, we would be using that in an assignment statement to assign it some variable. Otherwise, you simply lose the object that was created. Right, and someone has said that exactly. Great. Then name and briefly discuss 2 object-oriented design principles. So this was like the first or second lecture that we actually had when we were going over what you guys had learned last year. And all right, there actually are some questions, some answers already. So encapsulation, certainly that's one of the ones that we talked about. We talked about that hierarchical organization and how that's done through inheritance, exactly that in Java. We talked about what else? Abstraction, and actually that was an important one because that led to the idea of ADTs. That if we apply the idea of abstraction to a data structure, we end up with this ADT, which is a description of its behavior without a concrete implementation. I believe there's one more, and you've actually been taught that. Okay, the polymorphism, I think we discussed that a little later when we're talking about the hierarchical structure in more detail. But one of the things that you learned from first year, first semester, is that we can write our code as just one giant block. Well, that doesn't really help us when it comes to code reuse. All right, and so we'd rather use modularity. That allows us to have code reuse. It also allows us to be able to change the inner workings, which is kind of the idea of encapsulation as well, though that's with entire objects. But you could discuss the same thing with methods, that modularity allows us to change the implementation of a particular method and for it to still work within the code as long as it still follows the same logic, right? It has the same return types, accepts the same parameters, and so forth. All right, so any of those, naming and of course discussing those, you would have gotten an answer for. All right, then discuss inheritance within the context of Java and how multiple inheritance is achieved. You recall we said that Java doesn't actually allow multiple inheritance in the direct sense. You can't actually say that a class is a subclass of two different classes. Someone asked that good question, why don't we allow that? And in fact, one of the students answered that diamond problem, excuse me, that we can get ambiguity in terms of which inherited attribute or which inherited method needs to be called when a method is called within that base class. And yes, someone's already answered. The way that we get around that is by using interfaces. So we can have a class implement more than one interface, and so it can be of the types described in two different interfaces. All right, and a couple more notes. Process where a class acquires properties from another class. Okay, yes, that is inheritance. So you get a mark for saying that. If you want bulk inheritance, use interfaces. Exactly that. All right. And then the last one, discuss flow control within the context of Java, along with which statements can be used for explicit control. So we've discussed, branching statements, loops, different types of structures for flow control. But here we're asking you, well, what statements can be used for explicit flow control? So we don't have like a go-to operator like some other languages do to say, if something happens, then go to this line, or like skip this or repeat this based on that. Okay, we do have the loops for that, but we can't use a go-to statement to directly do that. Okay, someone's already given the answer. We can use a break or continue. And what's the difference between break and continue? That isn't asked here. So we use break a lot within our switch statements because we know that with a switch statement, it's not simply the code that's part of the satisfied condition that is executed. Everything after that is executed. That's how we use that break statement. So a couple answers here. Break breaks out the entire loop. Yes. Continue breaks the current iteration. That's exactly right. So if we have a break statement there, then we break out the entire loop and execute the code that appears after that loop. Whereas with the continue, we break the current iteration and we start the next one. So we still continue the loop if there are more iterations to be done. Which is the best method defining a node class, an inner class, or as a normal class? All right. If you want to use that node class again, then it should be in its own class, as in a file with that same name, so that you can use it in other code. So if we're going to use our node or the same node for a linked list and perhaps some other type, then we want to define it in its own file so that we can use it in different places. If, however, it was closely associated with that class and would only use in that context, then we would use an inner class. We could also, as we do with positions, define just the behavior that we want any position to have, and then the types that actually implement that may have additional behavior. So although we use positions in our node list or positional list, whether that is using a single linked list or a double linked list underneath, and we also use the idea of a position within our tree structures that we discussed now. Those are all the same idea. They're all positions. They can all simply return the values or the elements that are stored within those positions. However, if we create a node that implements position, then that will depend on what we're going to use that node for. So if we're going to create a linked list, depending whether it's a double linked list or single linked list, that node that implements position will have that element method, but it will also have a next and possibly a previous method. If we are implementing this position to use within a tree, then it will have, again, that element method, but it will also have to have a parent method. If it happens to be a binary tree, a left child and a right child method. Right. What is the definition of flow control? Okay. Well, in the simplest way of explaining it, it's the order in which statements are executed, and that would suffice. If you say flow control is the order in which statements are executed in a program, that would suffice. Code that is executed in the order they appear. All right, so you can put a little nicer, but it's exactly that. Okay, I trust that was actually a good little reminder of the things that we discussed before. Now, primitive counting, okay, we've discussed that a little more recently. And actually I should note, you should talk about that break and continue, and return as well. Return will actually break out of that method and return whatever value to be or reference to the method that called it. But you could also get marks for discussing the types of loops that we talked about, and also conditional statements, so while loops, for loops, for each, and then conditionals, if statement, and a switch statement. Okay, so consider the following function using primitive counting. Express the runtime of this function in big O notation. So let's see who wants to take this on. So for each one, let's go. I will just switch to a pen. And whomever pleases may give us an answer for that first line. So how many primitive operations are actually being carried out in that first line of the code? That's line 2 I'm talking about. Someone says 4, another says 5, another says 3. Any other answers? 3. 2 plus n squared. We're actually getting closer to the answer. Right, so I agree with the n squared for that new int nn, because we're actually creating n arrays of capacity n, and that means n by n squared elements are actually being set to those default values, which is set as part of the process of this new operator. There isn't actually an explicit constructor for array types, so it's simply those n squared statements. Then when that reference is returned and assigned to this variable trans, that's another primitive operation. Then the creation of trans would be another one. So it would be n squared plus 2. All right, and that's the n squared. Okay, that just requires a little bit of thinking, but the other ones we have agreed on. That declaration of a variable, that's a single primitive operation. That the assignment of any value, which in this case happens to be a reference to a variable, that's another one. So all in all, we have n squared plus 2 operations just in that first line, on line 2. All right, let's actually write that down so we're all on the same page. Or 2 plus n squared, if you prefer. All right, and that's what's been asked, but okay, that's already there. So for line 3, how many primitive operations do we see happening there? This is a for loop. So for our loop header, we're already going to have some statements that are executed only once and others that are executed a certain number of times. So let me say I would expect there to be some number plus, before we even agree on how many iterations, some other number that have done some big enter. Okay, there are actually quite a few answers already. Everybody agrees that 2 is the number of operations that are only being done once, so that would be declaring I and initializing its value. Yes, I'll agree with that. Then, before I even want to agree on what that big N is, the number of ones that are being done each time, there is that comparison of J to N. Nothing's being evaluated on either side, so I would, sorry, no, I to N. So that would be a single operation. Then the incrementing of I, we agreed, is 2 primitive operations. So I agree that that would be 3 done each time the loop is executed. We have a nested loop. Recall that we agreed that whichever has the higher number of iterations, we'll take that as number of iterations for each of them. So we actually shouldn't decide on what N is just yet. All right, we should actually look at line 4 then. So in line 4, again, it's a loop header. We'll have things that are being executed some number of times, just once, but all of those will be done N times. Go to within that loop, and then big M times some number of operations. So again, which number of operations are only being done each time that this loop is recreated, and then other ones that are being executed each time that the loop is iterated. Okay, so some are being done only within the outer loop and others within that inner loop. Okay, I see some discussion about whether it's n minus 1 or n. We'll get to that. For the inner loop, we have this variable j being created and then initialized to 0. So again, we have 2 there. We have that comparison of j to n and j being incremented. So again, we have 3 there. So there's 3 here, and we had that 3 there. Now we want to consider which is larger, n or m. The outer loop goes from 0 up to less than n. So that would be n of them, right? Because let's leave that 0 out. 1, 2, 3, 4, up to n minus 1. The ones from 1 to n minus 1 are really simple. There's simply n minus 1 of them. Then we add 0 to that, we get n of those. All right, so this one here is actually n. But before we go ahead and start substituting, we look at what's going on within our inner loop. Our inner loop goes from 0 to less than n, so it's actually the same amount of times. All right, 0 up to less than n, which means the greatest integer there is n minus 1. So again, we have n. They're the same. We can go ahead and substitute those directly in there. So we end up with, oh, actually, this was incorrect, wasn't it? So we corrected that this entire thing is within that. All right, so let's substitute our n's into that. For line 3, we end up with 2 plus 3n. Quite a few had said that, so that's what you end up with there. Let me write that down. 2 plus 3n. All right, for line 4, a little more complex. Let me start substituting in there. I end up with 2n plus, let's see, 3n squared. Right. Then what's happening within line 5? We said indexing into an array is a single primitive operation. We said assigning a value to a variable, again, is a single operation. So how many operations are happening at line 5? How many times are we indexing into an array? And how many times are we assigning a particular value to a variable? Note that whatever we come up with has to be multiplied by n squared because within both loops. Right, someone says 4, that's quite close. I would agree that this part is indexed into an array twice. Remember that a two-dimensional array is an array of arrays. We first index into one, which gives us a single-dimensional array. Then we index into that array. Then on this side, exact same thing is happening. Two operations, indexing into an array of arrays that gives us a single array, and indexing into a particular cell within that array. So that gives us two over here, two over there. That gives us four together. And then that assignment statement will be the fifth one. So that would actually be 5n squared. I believe, there we go. Someone had answered the 5n squared. Someone already answered the 5 actually a minute ago. So we agreed on the 5, and the multiplier is certainly n squared. Then with the return statement, this one we agreed regardless of where it occurs, that would be a single operation, even actually if it occurred within our loops. The line tries listing oh, thank you. Yes, it is. Right. So then let's count these up. What do we end up with? We have, let's just write that all together and then we'll sum those up. I have n squared plus 2 plus 2 again plus 3n plus 2n plus 3n squared plus 5n squared plus 1. So remember, we look at all the things with the same powers of n. I have 1 here, 3 there, 5 there. That gives me a 9n squared. Then for our n's, I have a 3 here, a 2 there. Okay, I end up with a 5n. Then for my constants, I have a 2. Another 2 gives us 4, and a 1 gives us 5. All right, is that the end? Yes, we're indexing 4 times. On the left, we're indexing twice. On the right, we're indexing twice. So that's 4 operations. And then the assignment operation is 2. So it's actually twice. We're simply adding all of those. Less than or equal to C. Oh, okay. So you're already answering in terms of our definition of big O notation. So you're saying it's bounded from above by some constant multiplier of n squared. Yes, that's correct. All right. And if we asked you, which we easily do, to prove that a certain function, let's say we give you this function, prove that it's O, big O something, then you would have to find an NO and a C such that, as you have it there, C, or this function is less than or equal to Cn squared for n greater than or equal to n0. All right, so good. We don't have to prove it here. Here, we just want the answer in big O notation. And I tell you, every year, people lose marks just for that part. So you've done this lovely analysis. You've gotten all those correct. You get 3 marks for all that. You've summed them up correctly. You get another mark for that. But you lose 2 marks because you don't tell us what the answer is in big O notation. All right, and you're told to express this runtime in big O notation. So my answer is, what is this in big O notation? Already have some answer how to do this. We drop constants and lower order terms. Okay, both of those are lower order terms. So the lower order terms include the constants. Good. Oh, okay, constant multipliers. I think what you're saying there. Yes, and lower order terms. So that means we get rid of these. Those are lower order terms. We get rid of that constant multiplier there. And yes, I'm already given the answer. We end up with big O n squared. All right, and that gives you 2 marks out of that entire 6 marks. So it's important that you don't stop at the point where you've counted the primitive operations and you've summed up how many there are in the entire method. You have to give the answer as requested in big O notation. All right, and those are actually some good examples of different ones that we haven't explicitly looked at, but we have agreed upon, like indexing to an array, but here into a 2D array, and creating an object that is initialized more than once, like an array where each cell within that array is initialized to a default value. And in fact, in this case, a 2D array. So it's n by n that are initialized to that value. Will the paper be uploaded? Let me do that now so that those of you who actually want to work on it or look at it on the side there can do that as well. Okay, so just give me a moment. Okay, I trust that none of you will by mistake download this test into it when we have our test in a couple of days. Okay, so that's done. The test is on there. A couple more questions. Can we get another paper? I think this is actually quite a representative paper. I looked at this one the year before that. The year before that, we hadn't gotten as far. So there was like one question to do with trees. The rest is quite similar, so that isn't representative. And before that, I wasn't teaching a module. So that really won't help you. Previous lecture didn't ask the same questions at all. Right. Oh, then there's another. Is the new keyword an operator? Yeah, it's just called the new operator. Like all operators, it actually implies some operations must be done, and it's those three that we agreed upon before. How different will this paper be, or our paper be to this one in terms of difficulty? It should be it depends what you think of as difficulty, right? If you are better at memorizing theory, then it'll perhaps be more difficult because this will definitely be skewed in favor of application. If, however, you don't like or aren't really good at that, but can easily apply when asked, then it'll be easier for you. If you're good at both, then it'll be the same. Because certainly the outcomes are the same, as in we're testing for the same things. The content that's being covered is the exact same chapters. So it should be the same, even if the questions are different and even if they're skewed towards application questions rather than theory ones. Okay, let me clear the annotations here so we get started on question B. Okay, then for B, which kind of growth best characterizes each of these functions? Okay, read all the table in the answer sheet and put an X in the appropriate cells. So here we have it already, and we can annotate right here. What do we think each of these are? So we have 5 functions that we're given here. We have 4 different types: constant, linear, exponential, and polynomial. And for each, let's simply put an X in the correct column. So for the first one, okay, someone's already jumped ahead. For the first one, I'm glad because of the first one we have 2 different answers. 2 say this is exponential. 1 says polynomial. Okay, now 2 says polynomial. So it's even, I guess. I would agree with the polynomial. Recall that exponential means that the variable is in the exponent. All right, 10 is a constant. So you remember your binomial theorem, right? We do binomial combinations of 10 and I to figure out what the coefficients are, but our variable will have, well, depends on which convention you've been taught, but mine would be increasing powers from 0 to 10. All right, regardless of that, this is binomial. So that's the correct one. Then the second, which is just 2000 and does not actually appear there, I would say that that is constant. Trust would all agree on that one. All right, then the third one, what do we think that is? I have exponential, poly, exponential. I'd agree it's not constant, right? We do have a variable n there. It certainly is not linear because we don't have n with a power 1. Our variable is actually an exponent, so it is exponential. All right, and of the 5 answers I have, 4 is actually exponential, so that's good. We're on the same page. Those that didn't answer that, just make sure that you go back to those couple of slides that we discussed this and you're comfortable with that. And then for the fourth one, 2/3n, linear. Yes, doesn't matter what constant our coefficient is, even if it was something irrational like pi. The highest power of n there is 1. It's not in the exponent, so we have linear. Then log 2. Where would this fit in? Yes, I'm glad. Okay, so one says exponential, 3 or what depending that came through, but I think 3 said constant. And yes, it will be a logarithmic function if our variable was the log of, or rather if our term was the log of some variable, right? However, it's log 2. It's a constant. In fact, we can answer what log 2 is. Because we're working computer science, the assumed base is 2. So what is the log base 2 of 2? To what power do we have to raise 2 to get 2? Great, everybody said 1. And then someone actually commented a bit tricky if you quickly scan. Yes, the idea is that you should read and think and not try to do it very quickly. You have about 1.2 minutes for each quest, for each mark, actually. So you should have spent a good 6 minutes on this. And that's certainly enough time to think properly about each one. So we will have that log base 2 is a constant, and everybody has correctly guessed that, or not guessed, but decided that that is 1. How long the paper? 45 minutes, 100. All right, so it's 100 marks. So by convention, we have 1.2 times the minutes of that, so you should have 120 minutes. However, we'll also allow for an hour of upload time. So it actually is a 2-hour test, but you get an hour extra for upload time. Okay, and actually a good question there. All right, so let me just put their constant. And the question that was asked is which runtime is fastest, I guess, between those functions. So actually, let's say a question that's asked is, let's put these in order. All right, so the growth rate of the runtimes of these functions, or the growth rates of these functions, which can represent runtimes of methods. Let's put these in order from slowest growth rate to fastest growth rate. Some said linear, some said constant, the first one. Yes, the first one should be constant. The second should be linear. Then the question becomes, is exponential a polynomial which has the faster growth rate? Then we have here, okay, some did actually give it exactly that, polynomial and exponential. Remember, we even took a look at specific examples to prove to ourselves that functions with a growth rate in runtime that is exponential are not actually feasible, because whilst for small inputs, they are rather quick, for large inputs, and by large we mean, not a magnitude of hundreds or thousands, it gets ridiculous, and so it's not. 2 last questions. In case of load shedding, what is the procedure? We will then extend the upload time. Depends on power, I guess. So I would say, if there's any doubt, because obviously some areas have been without power even now, even though we're not experiencing load shedding right now. If there is any doubt, rather go to campus. If you're not on campus, make sure all your devices are fully charged, because you will really only need to go online twice. And then, of course, have Discord on your phone, but that's not going to kill your battery power. so that you can download the paper and then work on it offline. Right? Work it on paper and pen if you choose. That is quite fine. Then at the end, you'll snap a shot of that. You'll use CamScan or some similar application to put that into a nice PDF, and then you upload that. So the work you should do is actually to make sure that you have the applications on your phone, have your devices fully charged and all of that. Okay, someone asked about logarithm. So you tell me, would a logarithmic function fall between these? Depends which log, sure, yes, but we're saying in general, where do logarithmic functions fall? Because certainly polynomial functions, it would depend which power, but we can still say that their growth rate is greater than linear and less than exponential. I remember we looked at that. We looked at a very high power of a polynomial and a lesser exponential, and we saw that actually at some point that exponential will overtake the polynomial. There is no power such that a polynomial function with highest power, whatever that power is, will always be greater than an exponential function. Okay, well, let's have a look at a few answers or questions. What online diagram tool can we use to draw trees? You can use really any general purpose one for drawing, any diagrams, Lucidchart. If you go to Mr. Blau's website, because these are used in third year a lot, he actually has quite a few. Let me just try to remember that URL. It was uml. I think it was blau.net. Let me just confirm that. No. Yes, okay. So if you go to UML, at the bottom of that first page, he has a comparison of different software that you can use for drawing UML diagrams. And that also works for our type of diagrams because a lot of those simply have generic lines, shapes, whatever it may be. You can choose whatever you want, really. I mean, you could use Microsoft Visio that comes with Microsoft, or you can download for free. Okay, all right. Someone already gave an example of one. You can go check that one out. Oh, yeah, someone's actually answering the question I asked. Log n falls between constant linear. Yes, that is correct. So let me just undo that. So if we're looking at what we're discussing here, where we had that slowest was constant, then linear, then polynomial, then exponential, we would say that log would be something like 1.5, right? So faster growth rate than constant, slow growth rate than linear. To accept LaTeX uploads, well, you would have to compile that LaTeX into a PDF or PostScript, but PDF, because we can't count on the fact that your marker will have a PostScript to PDF converter. So LaTeX source code, no. The PDF generated from LaTeX, then yes. Can you draw using ads? Yes, you can certainly do pen and paper. And in fact, a lot of students do that. Typed submissions for all the written answers and then hand-drawn diagrams. So that is completely acceptable, but we want a single document at the end. Remember, the hour that we give you is not for continuing the test. The test has the same number of marks, so you have the same amount of time. It's for compiling and uploading your submission. So you should take those pictures, take the PDF that you have, combine them into a single PDF. That's what you submit. But also we will beforehand release the honesty agreement. You also have to fill that out. You can sign that digitally if you have. If not, you can put in your name and the date, and then you will include that in the zip file that you are submitting. We expect to find a single PDF with all your answers. and that PDF of the honesty declaration. Would be required to draw diagrams in the test? Yes. Right, at the very least, we'll ask you one diagram, so you will be required to do that. Right. So let's continue. Let's see if we have any others that are of interest to us. Okay, this is very interesting. So, provide Java source code that represents an iterative version of the following function. Okay, that implies there's not an iterative function that instead is recursive. Is it? Yes, indeed. We see here that we have a recursive call there. Right. So, who would like to attempt this one? Okay, you don't actually have to give the answer. If you want to describe how one would change this type of recursive function into an iterative one, and that certainly suffices. If rather you look at what is trying to be done within this and you think, okay, well, I could do that some other way, either of those will be accepted. You'll recall when we were talking about recursive functions, we talked about different types of recursion, and we said that this type, where the last statement to be executed is that recursive call, is very easy to turn into an iterative function. You simply replace that recursive call with a loop. Then you can decide. Would it be better to have a while loop or a for loop? Are we doing this fixed number of times that we know a priori, or are we doing this based on a certain condition? That can decide. All right, so we have an answer here. You've chosen to use a for loop. You're going from int I equals 0 up to, all right, I see, you just want to have I less than n, and you're incrementing I each time. All right, then what are we doing within our loop? So you say there, we first initialize part to 1. That is a good initial value since we're going to be doing multiplication. Then if n is equal to 1, return, okay, so you keep that same base case, good. Then otherwise, you are each time indexing into, okay, the one thing I don't agree is that index that are n minus 1. You're in a loop. You should be using I to index through your array, right? Or rather to index into your array and go through your entire array by incrementing the value of I. So that should be I, but your multiplication and then a multiplication of that with product and assign it to product will indeed give you the entire product at the end there. Right. Then another says iterator int my iterator equals to array.iterator. Okay, what's that going to help you? You're still going to have to then give us that for each loop within which you are going to figure out that part. All right. Can we have there? We are multiplying each time by I minus 1. Okay, it depends where you initialized I, but yes, that could make it work certainly. Then increment I. Okay, the one we're using literals here, I'm a bit concerned. In fact, that looks more like a recursion trace. Or are you actually giving us the recursion trace already? Okay, you've jumped ahead there, but yes, the recursion trace is the next question. All right, we've already gotten a few right answers, so I will leave it there. Yes, a for loop is the easiest way. So you could have a for loop where you're using an integer I that starts from 0. I'm just using pseudocode rather. Your condition, you're checking that I is less than the array's length, and you are increasing I each time. And within that, you are taking product and you are assigned to that whatever the previous product was, multiplied by the current the value stored at the current cell within our array. Okay, it isn't actually, it's ARR, and using I to actually traverse that array. All right, that works. Even if ARR simply had a length of 1, then this would still work because I starts from 0 up to less than that 1. So it would iterate only once and would simply multiply product by A0. All right, but the easiest way is really to leave everything else the same and simply change that last recursive call to that for loop as most of you did, which is correct. One asks, could you look at it in the reverse way? Certainly. You could rather start at n, and remember this condition and what you do for each one aren't restricted, right? And in fact, you could have more than a single variable being changed each time. But yes, you could rather look at it as long as I is greater than -1, perhaps, and you start I at that array length -1. Okay, and instead you are decreasing the value of I by 1 each time. Certainly is. All right, then the recursion trace. So considering the recursive function given C, so the initial function that you're given, draw a recursion trace for product A4. So an array A, and we want to calculate the product of the first 4 elements within that array, because that's really what our function was doing. For that, given the array 1, 2, 3, 4, 5, what would that recursion trace look like? Okay, so who would like to start us off? To recall our recursion trace, what it looks like. Let me start with this. We have some function calling that, and then I will leave it to someone else to draw that first block that we have. Okay, you don't have to put it in the chat, rather draw it directly on the page we have before us so everybody can see what it should look like. All right, yes, I agree. It will be product. And what arguments do you pass to product? I'm not quite seeing that second one. I see the A. Second one, I'm not quite seeing it. Yeah, our expected would have our, let me just add this. It would have a little block there that represents that method call. I see that this is an A. What would your second argument be? Yes, okay, excellent. Then does this actually return something? Okay, you already answered that. No, it does not. It does another call, so it does a recursive call to product with the arguments A and 3. Excellent. Is there a specific way to draw recursion trace? Yes, there is, and we agreed on this. Please take a look at those slides where we discussed recursion. You should be drawing it a specific way. We don't have quite enough space here, so I see that's why you're going to the right. We'd expect that each one will be below the other. And we keep doing this until we have one that actually returns a value. And of course, if it's a proper recursive function or valid recursive function, just check that argument doesn't seem to be correct. It shouldn't be A2, yes, A1. Then that actually satisfies our base case. Okay, and what is ARR0? What's that index 0 within the array? Okay, so yes, 1 is actually what's returned. That gets returned to the calling function, which was actually calculating something multiplied by 1. All right, I expect it to be the other way around though. But yes, and that returns the one that called it. Again, I'll expect 3 times 2, but yes. Six times 4 gives us 24. Yes, and that's what gets returned to the calling function, is 24. But I agree with just about all of this. The only thing I don't agree with is this over here, that this is not a recursive call, so you shouldn't have this block around it, okay? Rather, you should simply have its AR0 or directly just say that's equal to, 1 there, and then it starts this return. Okay, so if you don't write PA0, it'll still be fine. Well, the thing is, what would PA0 do for us? Because the base case is n equals to 1. If the base case was n equals 0, then we'd do our recursive calls until we get there. But as soon as we get to this call actually returns the value 1. Right? It goes into that part because it satisfies our base case, and it returns 1. You have to put this part. I'm saying this returns 1, then that allows you to calculate this, and that gets returned to this one, that allows you to calculate that, and so on. What you don't need, I was saying, is this part, because that is not a valid recursive call. Okay, thank you for that. And that is correct as it is now, and that's what we would expect. You get marks for your recursive calls, and of course the correct answer at the end, but you also get marks for the structure of this. So you only get like 3 if you did everything correct, but did it just purely with text, and you weren't drawing the recursion trace, because that's what you're asked, to draw a recursion trace, not to simply tell us what the answer for this would be. Okay. Then we have some more theory ones, so we'll just quickly go through these, discuss the structural differences between a single linked list and double linked list, along with advantages each linked list portrays. If someone would like to put that answer in the chat for us, we can decide whether we agree or disagree. And for the next one, provide code or pseudocode that could be used to implement the add before method of a doubly linked list ADT, which adds an element of type T into the list before node n. It's also type T. This one, you wouldn't really get something like this because, again, you could simply look this up. You have the add before code or pseudocode within our notes, so you can really just go and look those up. Okay, I think in fact at this point it'd be more important to know that one in A rather than B, because B you just look up. Okay, and someone actually answered. Single linked list has only next reference, or next item say here was W has previous and next. We can refer to the runtime operations. Okay, yes. So you could refer to runtime operations, say that while most of the operations are constant for a single linked list, for our definition of a list, the W linked list is constant time for those operations. You could say, well, the single linked list actually uses less space than the W linked list. All right. For the sake of time, can we skip the theory parts? All right, but you still should know them. Why are stacks not used as often as a queue? Well, I don't know what you mean by used as often. I mean, we talked about the fact that the Java virtual machine actually uses a stack um, for recursive calls. So yes, we may not explicitly be using it in as many examples, but that's a very significant use of it, I would say. Well, why are queues used? Well, a lot of times we end up with situations where we have requests coming in and we need to service those requests in a very general sense. Whether that is requests for access to some resource, whether that's something like a printer spooler, whether that's within a buffer where we have a difference between our service time and the rate at which we are have those coming in, because a lot of times you follow that FIFO principle, a queue gets used because that comes up. That's it. All right. Someone says we won't have questions. Yes, we will ask a couple of theory ones that require you to think a bit, but we wouldn't ask ones like a method that you could go straight and give us our own answers from the slides and get marks for that. Okay, so we're doing application-based paper, let's get examples on it. Well, everything that we've done where we've actually written out the answers, the big annotation one, the one where we're comparing functions, all of those you will get. All right, consider the following list interface and write a queue that makes use of the list interface and the data design pattern to realize a stack ADT. This you could get, right? We had this in a prac. We could give you a slightly different version of that, perhaps it give you a different interface, because we've looked at different list interfaces. As I said, the previous text uses add before and add after, whereas the current one uses add between. Anyway, regardless, so we could give you a interface like this that describes a list, or rather we could give you one that describes a concrete implementation, perhaps a W-linked list or something, any type of data structure, and ask you to use this adapter pattern to implement the behavior of some other one. So it asks you to be able to use that adapter pattern, which takes an existing data structure and uses that to create the behavior of another one, right, to satisfy a different interface. And certainly that is some application. Next question, for C, do we need to write each method? Well, yes, you do, but the idea is that because you already have, well, by methods, as in the methods of a stack, yes. So our push, pop, top, you'd need to implement those, but you're using a list that has all of these. Right? You're told that the list satisfies this interface. The list already exists. You have to implement these. So use the list that you have to create the behavior of a stack. Are there other patterns you can get? Yes, there are other patterns you can get. Let's see, what else have we looked at? Oh no, we actually haven't looked at other ones just yet, right? We did just now discuss that template one. We haven't actually worked with other ones specifically, so at this point, no, not really. Yes, the visitor one, when we get to that, but at this point, not really. All right, we're being asked to rush ahead and not do the theory ones. So let's see. This is an ACT positions rather than nodes, all right. Okay, I mean, this one you should know, though, that would rather ask you to, what could we ask you here? That calculation that we went over. Because certainly with your text as a reference, you could give us that proof. How to the iterator? No, that would be too easy. Sequence ADT specific methods, again, you could just look that up. Okay, what is the maximum number of nodes in a binary tree of height h? Show of all your calculations. You may use a diagram to support your answer. Okay, you can ask something like this, so let's go through that. All right, first there was a question. What would 4a be? You recall we said that with positions, so even if the nodes implement, a node implements position, if we only expose the position, then whatever code is accessing that can call the single method that position has, which is element, but cannot affect the node structure. So can't change the value of the links next and previous or just next to a single linked list. So you cannot destroy the list by having access to positions only. You can destroy the list by having access to nodes. So that would be why it's preferable. There were some other things that we talked about, the fact that that's a good application of our encapsulation idea, that we shouldn't expose the inner workings, that we can then change the implementation of that node and it would still work. All right. He said they'll be exposed to dragons, all the dragons beyond. Everything they've been doing thus far. Right? Everything that we've drawn here, so our recursion trace, if we ask you to draw a tree structure, I mean, that's that, whatever you're asked to draw, you can draw it. So, well, the structure, I mean, I've said that in terms of the skew towards, or the lean towards application questions rather than theory questions, it'll be different. Structure as in, will the questions go chapter by chapter? No, not always. Sometimes because we use a lot of the ideas that we've used in previous chapters and subsequent ones, it's nice to ask them there. So you could have like a recursive function to do with trees, and we ask you to create an iterative one there. So it doesn't have to be chapter by chapter. We can certainly ask you things that aren't from a specific chapter or from multiple chapters within a single question. All right. So who would like to attempt this calculation? Maximum number of nodes of a binary tree of height h. Let me just simply give you the structure or how we could get to that. So the maximum nodes of any binary tree would be, well, if each node at a particular level has 2 children, right? That's the maximum amount of children. So if our root has 2 children, if its children have 2 children, if each of those children has 2 children, then we have the maximum number of nodes there. If any of these internal nodes have less than 2 children, and in fact, if any of the nodes at any internal levels, any of these ones, don't have the maximum number of children, the 2 children, then we end up with less nodes. So for a tree of height h, what we could realize is that our levels, about a level rather than a height. Okay, you could think of it the other around. Okay, since we have height here, let's use height instead. That here we agree to external nodes, the height is 0, 1, 2, all the way up to some height h. Okay, that at each point in our tree here, we end up with how many nodes? We end up at the top with 2 to the power 0 nodes. At the second one, 2 to the power. So at height h, we have 2 to the power. You could think of it as h minus h being the power. Then at the next one, it's 2h minus 1. Or rather, not h minus 1, h minus 1. Okay, but that just complicates things. Easier to simply say 2 to the power 0, then 2 to the power 1, then 2 to the power 2, then 2 to the power 3, and all the way up to 2 to the power h. Those are what we end up with. Then, oh yeah, sorry, h minus 1, thank you very much. All right, we start zero indexing going up to h, or rather, there are h many of them, we end up with h minus 1 there. Actually, I don't agree. Why is it h minus 1? The height is 0, then 1, then 2. The height of the root is the height of our tree, so no, actually this would be h. All right, can we add these up? Can we add 2 to the 0, plus 2 to the power 1, plus 2 to the power 2, plus up to 2 to the h? Yes, and there you go. Add the exponents? I would hope not. No, that's multiplication. All right, what we did realize is that if we put in the opposite, if we say 2 to the power 0, plus 2 to the power 1, plus 2 to the power 2, right? All the way up to 2 to the power h. This is the same as the binary number. Okay, let me write them apart so we see what we're doing here. This is the same as the binary number, a binary number with h1s. And if we're to add 1 to this, we end up with 1, 0, 0, 0, 0, which is 2 to the power h plus 1, but we added 1, so we have to subtract 1. Okay, some people were already on that path, but had 1 less power than required. So this doesn't mean that a tree of height h will have this many nodes. It means that actually that n, the number of nodes, will be less than or equal to this. If they're the maximum number of nodes at each level, as in the root exactly 1, the children of the root exactly 2, the grandchildren of the root 4, the great-grandchildren of the root 8, and so on, then we'll have this many. And so if any of our internal nodes have less than 2 children, we'll have less than that. But this is really the maximum of what we can get. So we know that n is somewhere either equal to that or less than that. All right, and whilst this took some thought, this we've done before. So as soon as you get to this, you start summing them up, then it should be straightforward. All right, okay, we're almost out of time. So let's just look at those as were requested that are application ones. Height and depth, again, you can just look up those methods. Define the tree traversal Euler tour. Again, you can just look that up. Here, we're asked to consider a tree, specific tree, and then we're asked to give the pre, post, and in-order traversal of this tree. So let's start with pre. With pre, we agreed that you visit the node before you visit its children, correct? So would visit the root first. If we call a pre-order traversal on this tree, then we start by calling pre-order on the root, and it will then recursively call pre-order on its children and visit itself in the order that we have agreed to. Pre-order, visit itself first, then its children, post-order, visit itself after its children. Great. So we visit the root, then it calls pre-order on its left child, which visits itself first, then calls pre-order on its children, left one, then right one. Then pre-order is called on the right child of the root, which visits that child before it then visits its child. So granted, you could draw this and put it out as I have asked, as I've shown here, or you could simply write down the order. It's a lot simpler actually. Just write down the order in which they visited. A, B, 1, 2, C, 3. So that'd be the answer for that one. Then the post, here someone's already answered that. 1, 2, B, 3, C, A. I agree with that one. That would end up with, we visit this one first, then that one, then this one, Then, am I happy with that? We visit this. Then we visit its child C, which would actually call 3 first, then C, then yes, I agree with that. Then in order is too easy, right? We think of a vertical line that's being passed across the tree. The order in which you hit those nodes with that vertical line is the order in which they should be visited. So that'll be 1, 2, 3, 4, 5, 6. Nice and easy. Okay, well, that's excellent. We have finished our allotted time. We've also finished the test that we wanted to review. So we'll stop there. We will start in the next lecture tomorrow because we can't fall behind, even though we do have that test on Thursday. Before anybody asks, no, there won't be a prac. So the first thing we'll do on Thursday is have our test. We will release the Honestly declaration beforehand, so you can already download it and fill it out, have it ready. But all that will be described in instructions. You must submit that along with your solution in the solution in a single PDF, that and the Honestly declaration within a single zip file with the correct name and convention uploaded to Eve before the deadline. All right, will the test be submitted on Blackboard or Eve? It will be on Eve. Facilitation will happen on Discord, much like we have for our pracs. If there are any errata, if there are any questions that the answer of which apply to everyone, we'll put a notice in that assessments channel on Discord, but also on Eve. I won't force you to do that. Could you please upload last year's SIG test? No, I don't want to do that. Can we not start at 1, but at least 1:30 because the engineering kids has power electronics? If you have classes during any of our classes, you should not be registered for this module. Please send me an email about that because I will have to speak to the course coordinator and possibly the lecturer for that module, because that is not correct. And we did ask you to tell us about that beforehand. So what is this? It's tight, but it's not a clash. Can it really be that tight? We start our tutorial or practical lecture at 1 o'clock. There should not be anything happening before that. All right? But I'm not saying out of hand, no. I'm saying please send me an email just so I can confirm what it actually is. And if necessary, we can decide in consultation with Prof. Nahar and let you know by tomorrow. So please send me that email as soon as possible. All right, thank you very much. We'll see each other again tomorrow. And please, if you found that there were some things here that you didn't know, as you found a little challenging, go and review those, please, before we have the test, of course. We will still have Prof. Nahar as a consultation today. I have one tomorrow, so you can also attend the consultation period before that. We also have, of course, our tutors available in the virtual assistant channel, so you can also answer questions there. Can we write and draw by hand? Yes, asked and answered. You may, of course. But then you shouldn't be submitting image files. You'll have to use an application like CamScanner to create a PDF from those images. All right. Thank you, and we will stop our recording.